Hi everyone, new video then. This one's on Newton-Raphson, comes under the heading of numerical methods. Now I don't know, because we change the planner all the time, where you're at in terms of numerical methods, so I'm going to assume you don't really know anything about it. So numerical methods, what are we talking about? We're talking about finding when graphs cross either each other or cross the x-axis. So when f of x is 0, and remember this only occurs when function crosses the x-axis, all right? When it crosses the x-axis. So sometimes that's really obvious. So when f of x equals x squared, take 3x, take 4, for instance, you can factorize that or use your calculator, and you'll know that x is 4 and x equals -1 only when this thing equals 0. If I don't write equals 0, it doesn't make any sense that these things are the roots, okay? Because this isn't actually an equation. I'm solving when it crosses the x-axis, okay? But if I had a function f of x equals x to the 5 take ln of x squared equals 0, because I'm finding when it crosses the x-axis, there's no way that I can solve this and get an exact value for x. I can't rearrange for x. I need to use an approximation. I need a method in order to do that, okay? And just to be clear what I mean by, because so many kind of students write a function equals 0 and don't really know what they're doing. And what do I mean by a graph crossing another graph? Let's say we had x squared equals x take x plus 3 or something, right? So x squared equals x plus 3. What I'm saying is, here's x squared, and here's x plus 3, right? You can see they cross at 2 points. So what we do is, you've got two separate functions here, remember? We bring it all over to the left, don't we, and set it equal to 0? So can you see that you create a new function, and you're still doing simultaneous equations, but you're doing simultaneous equations between y is 0, which is the x-axis, and your new function here, okay? So every time we set something to 0, we're using simultaneous equations between y equals 0, which is the x-axis, and the function we're talking about. But back to this, I need a different method then. I can't factorize it, I can't do anything with it. I have to have certain method to approximate a root where it crosses the x-axis. And the Newton-Raphson method is just one way of doing that. And there are a few ways, there are lots of ways of finding roots. But the Newton-Raphson is really nice. And every numerical method has flaws, so where it doesn't work, and it also has kind of a basis of its methodology. So the Newton-Raphson works through looking at tangents to curves. Okay, so what it is, alpha is the point, alpha is the actual root of this curve, but I don't know that. I don't know what it is. So I've got a general curve, y equals f of x, yeah? All I know is the curve itself and this starting point x0. I know the value of x0, which of course has coordinates x0 and f of x0, right? And I said this whole method works by tangent. So if I drew a tangent to the curve, it crosses the x-axis at x1, which you can see is much closer to alpha, right? So the idea is that if I find x1 and then draw a tangent at x1, can you see that tangent is closer to alpha and would generate a new value, x2. And I keep doing it and keep doing it and keep doing it lots and lots and lots of times, an infinite number of times. And eventually what will happen is, you see we've got alpha here, my tangent will just be on top of alpha. So I just keep getting the same value churning out again and again and again, because it's not moving anywhere, because the alpha is where the root is, and the tangent to alpha crosses at 0. So, well, crosses the x-axis at alpha. So it's just going to continuously give me alpha, and that's when I stop, because that must be the root. Okay, so we're converging getting closer and closer to alpha until when we get to alpha, it's just going to keep returning alpha to us. So, sounds a bit abstract, so let's see what I'm talking about here. First off, in order to find a tangent at this point x0, I need to know the gradient, right? So the gradient is change in y over change in x. So this is the y value of this straight line, remember, of this tangent. So I've got one point here, x1, 0, because the y coordinate 0, and this point here, so minus 0. x0 is our x coordinate, take x1. Okay? So if I times up by x0 minus x1 and divide by f dash of x0, I get this. So all I've done is times up and then divided by this. Okay? And then if I make x1 the subject by moving this x0, this f of x0 stuff over, can you see this is the equation for my new value x1? Okay, and you'll see what happens is if I take this value x1 and then do the same thing, so x1, f of x1, draw the tangent, which I did, and cross it at x2, and repeat the whole process that I started with, you'll see you'll get exactly the same thing, except it will be x2 equals x1 minus f of x1, f dash of x1. Can you see what's happening is the new approximation is built on the old approximation. The next approximation is the original, the one just before it, take away f of the one before it over f dash of the one before it. So in general, and this is what you need to remember, x of n plus 1 is the same as xn, take away f of xn over f dash of xn. Okay, where n is kind of your number of iterations, because x0 is your starting value, so the next one, x0 plus 1, remember that's subscript, that's low, that's a small n plus 1, so if n is 0, your next one would be 0 plus 1, so that's x1. Do you see? So this is your general Newton-Raphson method, and it comes from tangents, exploring tangents. So let's apply it to this example here. So this diagram shows part of the curve, and the curve has equation, it's not very big, x cubed plus 2x squared take 5x take 4, okay? It's telling us that f of x equals 0, so it has a root, alpha, in the interval 1.8, 1.9. So this alpha here is between 1.8 and 1.9. It says explain why x0 equals p, so that's this point here, right, is not suitable to use as a first approximation when applying the Newton-Raphson method. So this is jumping the gun on why this method isn't good in particular situations, because if I take that point P here, this is the stationary point. Remember, it's telling us that point A is a stationary point on the curve. So if I draw a tangent to a stationary point, you can see that that tangent's never going to cross the x-axis. So therefore, I'm never going to generate a new value of x. And so I can't, it's just going to give me a maths error. If the tangent was slightly over, slightly to the right of the stationary point, even if just subtly, the gradient will be such that eventually this tangent will cross the x-axis and therefore give me a new approximation which I can work with, okay? Which I can work with. But I can't work with it if the tangent doesn't cross the x-axis. So answer to A is it's not suitable because tangent has gradient 0, so it's a flat, and therefore will not cross the x-axis. Okay? Part B. So ignoring that, let's start with x0 equals 2. And that's another thing as well with numerical methods. You have to have a good starting value. And sometimes that starting value will totally screw you over. Or it can really help. And it all depends on the method, on like the numerical method that you are using, on how kind of accurate that initial approximation has to be. So it says That's my first approximation. Apply the Newton-Raphson twice to find the second approximation to A. All right. So it's asking us to use our Newton-Raphson formula, basically. So first I need to quote my formula. Xn plus 1 is xn, take f of xn over f dash of xn. Remember, the dash is on the bottom, okay? And we're going to write exactly what you need to write in your exam. Okay, so x0 equals 2 is your starting value. So my new value, xn plus 1, is the first one after that, so x1 is going to be x0, take f of x0 over f dash of x0. You see, you're using your previous result. So that's 2 minus, and then you have to write what you're putting in. So I'm putting it into f of x here. So 2 cubed plus 2 squared minus 5, 2, take 4, all over. And again, you'd have to write what the derivative is, because I need to know what f dash of x is. So f dash of x is 3x squared plus 4x minus 5. Okay, differentiating this thing here. So now I need to shove that 2 in there. So 2 squared plus 2, take 5 equals. Now it's a really handy function on your calculator. If you just type in the algebra of this. So if I type in, actually I can show you in class if you want. So if we type in 2 as the answer button, you can go for that. So answer cubed plus 2 answer squared minus 5 answer minus 4 over 3 answer squared plus 4 answer minus 5. 2 take that. I should get 28 over 15. So 20. I'm not rounding at this point because I know I'm going to need this for the second approximation. So we've done it once, but now we're going to use that with x1 to find the next value. So x1 we just found out was 28 over 15, and yes, I do need to write 28 over 15 cubed plus 2, 28 over 15 squared minus 5, 28 over 15 minus 4. So 3, 28 over 15 squared plus 4, 28 over 15 minus 5. So I'm going to use that value now. I will show you this really handy calculator thing in class to speed this up. But anyway, answer cubed plus 2 answer squared minus 5 answer minus 4 over 3 answer squared. And you're way less likely to make numerical mistakes if you use the method I'm going to tell you in class. So I should get 1.0467, and it wants it to 3 decimal places from the question there. So 1.047 to 3 dp. I hope I've written that in the calculator correctly. Okay, well, we'll see, won't we? And I'm so glad I double checked that, because I did put that in the calculator wrong. Okay, so it is 1.856 to 3 dp. Okay, now it's good. My spidey senses were tingling a bit because I knew from the question that the root was between 1.8 and 1.9. So just make sure your answer makes sense, okay? So I'm going to go to part C because it's a bit bigger here. So it says, by considering the change of sign in f of x over an appropriate interval, show that your answer to B is correct to 3 decimal places. So let me just get that answer to B back. So 1.856, right? Now, all right, so we've got that answer by considering the change of sign. So let's just think about what this is talking about. So again, this is another thing in numerical methods that you may or may not come across. So alpha is the actual root. So we're talking about this bit here, yeah, but I've just zoomed in. Alpha is the actual root. This is f of x equals 0. This is the x-axis, right? And at the moment, I'm saying alpha is 1.856. So what is it talking about by this interval and change in sign, right? I'm saying alpha is approximately that. So can you see, let's assume alpha is that. Then either side of alpha, so here and here, in other words, the upper and lower bound, So 1.8565 and 1.8555. So notice I'm going one decimal place higher than what I've got originally. The upper and lower bound, it's so important that you know that. The interval is the upper and lower bound, right? Can you see that if I pick 1.8555, I should get a negative value for y. And if I put 1.8565 into here, I should get a positive value for y. i.e., there's a change in sign. Because I've gone from negative, 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 and then bang, I've hit alpha where f of x equals 0, and suddenly my y value is positive. So assuming that it's continuous, i.e. there's no breaks like asymptotes or anything, then I must have passed through the x-axis in order to change from negative y's to positive y's. And I need to prove that either side of 1.856, i.e. between the upper and lower bound, that happens, and therefore my answer is correct to 3 decimal places. So all you need to do is you say choose interval, and like I say, that interval needs to be the upper and lower bound of your number. So 0.8555 and 1.8565, right? So I whack that in, 1.8555 and f of 1.8565. So I should be writing this thing in here. So I should be writing 1.8555 cubed plus 2 lots of blah blah blah. I have to write that in my exam, okay? I have to actually write that fully. But because of board space, I'm just going to go for it. So if I put that in, answer cubed plus 2 answers squared minus 5 answers take 4, I get minus 0.00347 blah blah blah, which is less than 0, which is what I expected. I expected a negative answer. And if I whack in 1.8565, 1.8565, but remember I have to write in, I have to 1.8565 cubed plus 2 blah 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 blah, actually put it in, okay, in order for you to get your method marks. So answer cubed plus 2 answers squared, take 5 answer, take 4, I get 0.009283, okay, and that's enough, which is positive. Can you see? So what we need to say is this. There's a change in sign. Hurrah! Which is exactly what we wanted, right? There's a change in sign. F of x is continuous, i.e. there's no asymptotes, and therefore that's not going to mess anything up. So change in sign, f of x is continuous, therefore root correct to 3dp. Do you see? It must be correct, because at one side, the lower bound, this thing is negative, and at the upper bound it's positive, so somewhere in between is my answer, and that's where the graph crosses the x-axis. Okay.